So before your test tomorrow, I want to give you an opportunity to see a couple of the variants, namely what happens if you end up having some holes instead of just vertical asymptotes, and what happens if a slant asymptote comes in and tries to kind of like be part of this party. So let's just jump into it. So if you're going to be doing this kind of function analysis, the very first thing that should pop into your mind is that you need to factor this thing. So before you try finding like asymptotes, discontinuities, whatever, let's just go ahead and factor. Now the key to knowing this can factor is realizing these are quadratics. And so we at least got to make an attempt at factoring. And so the top we have x and x to make x squared. Looks like we can use a 2 and a 3 to get at -6. And if we go plus 3 minus 2, that will be the plus x in the middle. On the bottom, the first thing we should probably do is take out this common factor of -4. That way we're looking at a cleaner quadratic which to factor. And so if I take a -4 out of each term in the bottom, we end up with an x squared. That will be a plus 4x because plus 4 minus 4 is -16. And that should be a plus 3 trailing because positive negative is a negative. 4 and 3 make 12. And so if I'm going to factor this guy now, the -4 will just be kind of hanging on to our problem. And then we factor the bottom. Let's see, we have 3. So 3 and 1 have to multiply to make 3. X and x have to make your x squared. And if we go plus 3 plus 1, we're going to have, excuse me, our factors. So now if we do a quick analysis, we'll see in the top we have this factor of x plus 3, and we do in the bottom as well. And so immediately we know that those are going to cancel, but let's not worry about that yet. The first thing we should do is list our discontinuities. And so if we look at the bottom of our fraction, we do have two discontinuities that exist no matter what happens with the function, because we have two factors, x plus 3 and x plus 1. And so we're going to have two discontinuities. One is going to be a -3 because it makes our first term 0, and the other one we're going to have will be a -1. Now notice I'm listing this as discontinuities very generically because I'm not haven't decided if they're going to be asymptotes or they're going to be removable. What kind of things they're going to be. Now what we can note is that since we do have this repeated term, those x plus 3's cancel out. Now this -3, x equals -3 is a discontinuity no matter what. But what ends up happening since we cancel it out of our function, this ends up being a hole. It's a discontinuity that we remove. Remember, a hole is the same thing as a removable discontinuity. Whereas x equals -1, that's going to be a vertical asymptote. Okay? And so what that means, if I come down to my graph, I know at -1, I'm going to have a vertical asymptote. It's a non-removable discontinuity, and so I know that's going to be a hard break in my graph. At -3, just a couple over, I know that I'm going to have a hole. I don't know where it's going to be yet. I'm just going to put it here temporarily, but I know at -3, my graph is going to lose a value because I did remove it as part of my my analysis with my discontinuities in my first block. Now, the thing that you may not realize is that from this point forward, since we canceled out that x plus 3, we can actually proceed as if it never existed in the first place. So when I think about my horizontal asymptotes, I can think of this function f of x, instead of thinking as a full function, just whatever's left. Just as the x minus 2 on top, since the x plus 3 has been canceled, and then -4 times the quantity x plus 1 on bottom, because again, the x plus 3 is canceled out of both terms. So this might help me find my horizontal asymptote, because now it's a much simpler function. I'll note that we have an x on top, x on bottom, same degree, which means we're just going to find a ratio. So that's going to be y is equal to -1/4. Now you can approach this by limits or by long division, but either way you do it, we're going to have a -1/4 for a horizontal asymptote. All right. Now we do need to figure out if it's crossing. Well, the whole point of knowing if it's crossing or not is just knowing if my function is going to take the same value as my asymptote. And so we're going to set them equal to one another. And so we have x minus 2, and then here we have -4, x plus 1, and we're postulating, could this possibly equal to -1/4? I'm going to assign the negative to the top of that fraction. It doesn't matter which. I just needed to do that to figure out what to multiply by and keep that clean. But we're trying to figure out if this even carries a value. So let's do some cross multiplication. And so we have multiplication this way, we'll end up with 4x minus 8. Multiplication this way, we end up with 4 times the quantity x plus 1, which will go ahead and multiply out as 4x plus 4. Now in solving, we can notice that we have 4x's on both sides, so essentially those cancel, and we're just left with -8 is equal to +4. Now remember, this is going to tell us if we're actually going to cross our asymptote, In this case, we're not going to because this is a nonsense kind of thing. Negative a can never be 4, which means this equation can never be true, which means this equation can never be true. So it does not cross. Nope. And so what we can tell in our graph is we have this negative 1/4 as a horizontal asymptote. So about, I don't know, about right here. And it's a hard break in our graph. We cannot cross this line. And so we're starting to get a really clear picture of what this could look like. Let's go into our last part. Let's figure out our x and y intercepts. Now again, we can do this with this function, the x minus 2 and the negative 4x plus 1, our reduced function, our depressed function. And so let's find our x-intercepts here. Let's find our y-intercepts here. So recall that the x-intercept is the value of y when value of x when y equals 0. And so we can set y to be 0 and solve our function. X minus 2 times the quantity negative 4, x plus 1. Now if we think of this in terms of cross multiplication, that will result in a 0. And so is this going to be 0 and cross multiply the other way is equal to x minus 2. And so if we solve for x, we actually are going to have an x-intercept as x equals 2. The y-intercept is going to be the y value when x equals 0. And so the y value when x equals 0, so that would be 0 minus 2 over negative 4, 0 plus 1. And so through simplification, we end up with negative 2 over negative 4. Our y-intercept is going to be positive 1/2. And so we can add that to our graph as well. And so at x equals 2, we're going to have an x-intercept. Okay, and our y-intercept is going to be 1/2. So let's zoom way in here. So our y-intercept is going to be right here. So you can probably get a sense of where we're going to have our graph actually be. But we have this really nice technique. Not entirely, oh, there it goes. Okay, so we have this nice technique using the infrawave. Now this is a new thing too. We talked a little bit about this at the end of the hour, but let's go ahead and do the infrawave. So right here is our x-axis simulate. That's our 0. Now that's not going to be an asymptote or an intercept. It's just there to keep in mind where things are. And now I'm going to fill in all the things I know affect my x-axis. So one thing I'm going to have here is an x-intercept at 2. And so let's see, 1, oops. So it's called about right here. And so that's going to be x-intercept. I'm using a dot to show that. Looks like I also have a vertical asymptote at negative 1. And so that's going to be about right here, which I'll denote using an x. I'm not going to map my hole because my hole isn't going to necessarily be on my axis. It's going to be where my graph belongs. I'm going to put a hole there. And so these are the only things that affect my axis. Now, if you look at the leading coefficients of our function, the x squared and the negative 4x squared, that has a negative overall value. It's a positive divided by a negative. And so in my information wave, I'm not going to start in the upper right, but instead I'm going to start in the bottom left, or bottom right, excuse me. So I'm going to start negative, cross through my first point, and then come through my asymptote. So what that tells me, leading right to left, the function was negative. Oops. Then through my x-intercept, it'll become positive until my asymptote, and then it'll exist only negatively. And so now using our infrawave, we can actually graph this in. And so starting at the far right, we have a completely negative function until I hit my x-intercept, and then it's going to go positive. And so here's going to be a little tight, but I need to be below the line, hugging my asymptote, because that's my end behavior, crossing through my x-intercept, crossing through my y-intercept, and then ending positive. So it's a very, very thin function, but it can't cross my asymptotes, because if you look at both cases, we're not crossing here, and of course we can never cross a vertical. So then after my asymptote, so we have like this region right here, is this region right here. After my intercept, before the asymptote, after the intercept, before the asymptote, and then after the asymptote, it's got to be all negative. And so this is going to be my green section, if you will. Now, it's all negative, which means I can't cross either asymptote, so the graph has to come from the bottom and then end at the top. So I kind of guessed that's where my hole had to be, but it turns out that's a pretty good location. Keep in mind that was a hole because we removed the discontinuity in negative 3. So right here at 1, 2, negative 3, we're going to have a hole. Not an asymptote, but it's a hole in my graph. So we can kind of track a couple things. It's nice to talk about our limiting behavior. So as x gets to infinity, my graph is going to go to negative 1/4, which we predicted as our asymptote anyway. The same thing here, as a limit goes to x, it goes to negative infinity, we're also going to end up at negative 1/4. Never crossing, but going right to the axis. And so the last step of this is now take our graph and evaluate our domain and range. Now here's where we got to be really cognizant of all the things we talked about so far, all the things you discovered in this problem. Let's start with domain. So we can predict our domain will have two hard breaks, or excuse me, two hard breaks. One is going to be the asymptote at -1. The other one is going to be a hole. The hole exists because we can't use -3, but it's also been removed. So the domain is going to start at negative infinity, travel all the way to our hole, which is at -3. We cannot use it. Start again at -3, go to our asymptote at -1, start again at -1, and then end up at infinity. Now these are all parentheses because these are all hard breaks. None of these are things that we can take as a value in our domain. That's why they end up as holes and asymptotes. In terms of our range, we can note that this horizontal asymptote, again, is a hard break. We never cross the asymptote, so here we're going to go from negative infinity to our asymptote value, which is negative 1/4, and then start again at negative 1/4, pass the asymptote, and head all the way into infinity. Okay? And so the thing to be careful about, or thing to note, is that if you have a hole, make sure that you're using and you don't really have to. Like, it would work if you use a full function even after you remove that discontinuity, but it makes it much easier, I think, as you're dealing with a much simpler function, is that after you remove that discontinuity, you use a reduced version of the function, okay, without the x plus 3 terms in there. Since you had a negative coefficient, the information wave starts negative instead of positive on the right. And then from there, you can just graph your regions, and you get your domain and range. So I'm going to put out one more video really quick here. That one's going to have to do with what happens if you have a slant asymptote. So that's going to be what you see next. Right? Thank you very much.